My name is Oleg. I'm co-founder at Outerbound. I'm going to talk today a little bit about the lessons we learned from orchestrating large-scale ML workloads, including GenAI, and data on Kubernetes, while helping our customers at Outerbound. And then Riley from Autodesk will talk about the more practical side of things, how they do it there. So the previous speaker actually did a pretty good job kind of introducing all the concepts, so I'm not going to spend too much time on this, but still, it's kind of useful to zoom out a little bit and talk about the kind of the full picture. And if you think about, before you even think about ML and AI, it's useful to think about what's even the difference between normal, traditional software and ML and AI. So with traditional software, you usually have those yellow hat people, engineers writing code, and that code gets put in this box. And it's some sort of valuable system that produces, in this case, money, so produces some value to your customers in the end, because we're talking about still applied ML and AI here. We're not academic conference. So what changes if you introduce ML, not even talking about GenAI yet? I mean, some things change. There's still this big box. There's still a lot of software. There's a lot of traditional code that you have to write. But now you have those couple new things. So you have this data box on the left that somehow, using some magic, this yellow hat or purple hat guy, data scientist or ML engineer, makes an ML model out of it. And now that thing gets plugged into your traditional software, still hopefully to somehow produce the value for your customers or power your product or some part of this product. And this thing is a little different because in the previous slide, you had this very deterministic situation where you just write code, you can write some unit tests and things like this. Now you have this more fuzzy cloud that is based on probabilistic principles, based on statistics, trained on data. So it's not as predictable, or it's predictable, maybe not as easily testable, but it still has to run correctly. It still has to plug somewhere. We're not building those models just for the sake of building models. And it has to work with the rest of your software. So looking at this slightly differently, just putting those boxes in the triangle, you have data, which is a new part. You have models that you train based on this data using some compute platform. And then, again, very important to remember, again, they have to somehow plug into your production systems, become features or something in your product. So they don't just exist in vacuum for you to write a paper about. And you have this little data scientist or machine learning engineer who has to work on those models and has to be productive. And they usually have a slightly different set of skills than your traditional software engineers. They know those math and statistics really well. They're also usually actually pretty good at software engineering, but they're not necessarily spending all day designing some beautiful architectures of message buses and things like this. So we want to make them productive, and we want them to be able to rapidly prototype and build those models iteratively and deploy them in production, ideally with as little help as possible. So that's probably the biggest goal if you're building any kind of ML infrastructure or AI or GenAI, even before you get this. And another way we like to put it is there are those two conjoined triangle of success of data scientists on the left who care mostly about top levels in this stack. So they care about modeling and maybe deploying their models and versioning. And then you have those yellow hat infrastructure engineers that mostly work on the lower layers. They build this data and compute platform and build some pieces for orchestrating those ML workflows. So really, the data scientists really care about the modeling part, and the infrastructure parts are kind of underneath this stack. So now closer to GenAI, does anything actually change with GenAI? Is it even different when you throw LLMs and GenAI and foundational models in the mix? And here, this is kind of just random, rough architecture of maybe your data infrastructure or ML infrastructure if you're starting to get into GenAI and LLMs. And I wouldn't say a lot of things change. There's emphasis changes a little bit on certain things. So if you talk about compute specifically, one big difference is that you now have those big GPU boxes to train from scratch or fine-tune your LLM models. And this is different probably from the, at least, philosophy that ML systems and data systems used to have like 5-7 years ago, where you would be talking about, Spark and all those kind of things, where you just have those very elastically scalable clusters of compute. You just kind of throw a few more cores into the mix and things become faster. Now you have, you actually have to have GPUs. You have to use, certain GPU types for certain models. It becomes, it doesn't change completely, but you have a lot more heterogeneous clusters in terms of instance types and hardware types. So that's one thing. Another thing that is always there for ML is that you have a lot of problems that maybe don't require a giant amount of GPUs or don't require a giant GPU box with like A100s or H100s, but you're running some sort of what they call embarrassingly parallel workloads. Let's say you want to run inference in a batch mode, maybe pre-compute some recommendations or something, embeddings, and your compute platform has to support that as well, which is pretty different. So this is more closer to Spark and things like this, where you have those super parallelizable tasks. And last but not least, these days for AI, a lot of times you will be relying on vendors and something like OpenAI API or something like this. It's not as exciting as running giant clusters of GPUs on your own. But you have to remember that this is also has to be part of your platform. It has to play nicely with other things in your infrastructure stack. So, and those tasks, they don't require as much compute resources, but they still have to finish, start on time, and the results maybe get plugged into your other models. And thinking about quickly from orchestration perspective is a few things here that are different. So one is it becomes really important to think about failure modes because, again, those large models are really expensive to train. They cost a lot of money. If something fails, you need to make sure that your data scientists or ML engineers can understand what went wrong and recover, and ideally not to lose too much compute budget. And another thing is it has to react to new data. Very few people here probably would ever train a foundational model from scratch. That means you're taking someone else's and you're fine-tuning this. And that becomes an interesting problem in versioning and organizing those pipelines because even though people were talking about fine-tuning models and maybe some sort of online training for many years, I would say if you asked me like 5 years ago, it's not really something that 99% of use cases would need because you could a lot of times just train from scratch, just train on daily data, retrain the model, and you would be probably better off. It may be not the most computationally efficient way to do things, but it would be a lot easier from an infrastructure perspective. Now that actually makes sense that you take the model from somewhere, you fine-tune it on your data, on some cadence, and that poses a set of new challenges for managing this data and results and models. So since the talk is titled Kubernetes, I'll be talking mostly about the compute part of this, and maybe getting closer to practical learnings that we got from this and helping our customers to run those models on our platform. First thing is, again, kind of easy to overlook is really the user experience for data scientists or ML engineer. Talking about Kubernetes specifically, it's awesome for people like me, infrastructure engineers. I love how they have this universal declarative configuration management language and all those things, lots of YAML. And it doesn't lend well for use by data scientists directly for a few reasons. So one is, I would say there's a really philosophical difference between Kubernetes that was built at least initially to run more like services, microservices, your usual web apps. So it's very natural for someone managing the cluster or configuring the cluster to use this awesome declarative language where you describe what you want end state to be, and it kind of happens for you. So you could say, I want the service to be running at this port with this host name, and things kind of happen, and you don't really care how it gets there. When you start thinking about ML and batch workloads, it's actually not really the case because it's not really about the end result. So end result is all your training jobs are finished, so nothing is running. So it's really about the kind of natural way to describe it, as you all do probably day to day, is to describe the steps to get there. And it's very imperative. It's not really a declarative thing. You're saying, hey, run this job, take the results, listen for this event, trigger a fine-tuning job when this data arrives. And of course, the other thing is there's a lot of YAML, and it's very technical and very low-level language if you're doing YAML customize or whatever. So that's where Metaflow comes in real quickly, because we're a company built around Metaflow. It's an open source project, open sourced by Netflix a few years back. And I think the biggest value is really it provides this very natural user interface, Pythonic for data scientists, where they can write their code in Python, not caring much about Kubernetes and all those things. And Metaflow kind of takes care of scheduling all those workloads on a Kubernetes cluster. You can version your artifacts. You can download data really fast from cloud storage. You can use parallel training and so on. Okay, there's no video. But it looks like this, but it actually runs. You can basically write your code, run it locally, and then with pretty much no changes, run out Kubernetes in a distributed fashion. Okay, the video is missing. And here it runs on the cluster. Another learning, or I guess a quirk, once you start running those workloads on Kubernetes, machine learning related, is the workload diversity is really huge. So if you just, again, you take your vanilla normal Kubernetes cluster with some services running in it, it's kind of one thing. You can have all those pods running, come up, auto-scale, all that stuff, collect metrics. Now you start throwing batch workloads, it's pretty different. Because they require a lot of auto-scaling up and down. When fan out on 100 tasks, then you want those tasks finish, you have some join step that sort of shuts everything down. It's very different requirements for the autoscaler and for scheduling. And maybe using cluster upgrades as an example. If you want to upgrade the Kubernetes version or you want to replace the underlying nodes, if you just run the services as usual, you can usually just add a few more replicas, shut down some old containers, start new ones on new nodes, and kind of off you go with high availability and all that. When you start having batch workloads, they're actually usually not really interruptible, so you cannot just spin another replica of a batch job that trains a foundational model for 2 days or 3 days or whatever. So you kind of have to wait for it to finish before you can do anything with the underlying node. So kind of the good news is that they don't run forever. Every batch job at some point stops. But if you really want to have high availability for your data scientists, and it's important because it's so expensive to use those GPUs, your cluster upgrades could easily take days or weeks if you want to really do the rolling gradual replacement of those nodes without interrupting anyone. And in addition to this, there is also something we provide is cloud workstations where data scientists' kind of workspace is not on their laptop, but actually in a remote node in a Kubernetes cluster, which is great because they get access to all those fancy GPUs directly. But it also adds a lot of requirements on scheduling. Again, you cannot interrupt those things very easily. Next thing, again, it's not super fancy, I would say. It's just something that you run into almost immediately is container image sizes and managing those sizes. Because when you start dealing with ML workflows, I did a small plot here of PyTorch transformers container image from Docker Hub from Hugging Face. So you can see a few short years, it went from 2 gigs to 8 gigs. It's actually not unusual for us to see images in like 10 gigs and even 20 gigs range, especially when people start to try to build some sort of universal image for their data scientists. So they add PyTorch and TensorFlow, and they iterate on those images. So you can imagine you start a pretty small parallel training job using this new image, and it's just 5 nodes. Now you have to suddenly pull 100 gigs before anything useful happens at all. So that becomes a problem both from performance and actually it makes user experience really bad if they have to wait every time for 5–10 minutes to launch whatever they're working on. That kind of hurts productivity a lot. And in terms of solutions, there's some solutions in open source, like an open source project, I think it's CNCF Harbor, that provides in-cluster image caching, but it's easy on the surface, but it gets really complicated when you get into details. So as a kind of an example of that complexity is, if you run your cluster on, let's say, AWS, in a lot of cases, you probably want to run it across availability zones, and it's not super obvious from the pricing on the Amazon's page, but it's actually, you pay pretty much as much cost for networking across availability zones as much as you pay for cross-region data transfer, and they really charge you through the nose for those. And especially if something like a NAT gateway is in the middle, it gets expensive, and you're kind of pulling those gigabytes and tens of gigabytes and terabytes of data just for container images. So you have to have your, if you do in-cluster image caching, you have to make sure it's availability zone aware. And now to the kind of the fun task is running multi-node, multi-GPU workloads. It's also not supernatural thing that comes out of the box with most orchestration platforms, including Kubernetes, because you do want this gang scheduling semantics, which means if you have a highly parallel job, you don't want to just schedule 100 tasks. You want them to run concurrently and communicate with each other to share parameters or something. And it's crucial, especially now with like those large models that sometimes don't fit on a single node. And there are a few open source solutions like Q and Jobset and Volcano. I think Kubeflow has a few operators, but it's still early days. When you start using this in Anger, you run into a lot of quirks, and it makes things more complicated for the scheduler. Autoscaler, whatever you're using, cluster autoscaler, or maybe something more modern, it's not always aware of this. And when you add this and also your normal workloads running in the same cluster and normal batch workloads and those workstations, that again becomes pretty tricky. And lastly, one big problem that everyone runs into if they want to train those foundational models is just scarcity of GPU. There's just not enough GPUs on major public cloud providers. They cost a lot. There are some alternative providers coming up, like CoreWeave, for example, that are specifically focused on GPUs and provide more competitive pricing. But now you're in the situation where maybe most of your infrastructure runs on your traditional public cloud, and you kind of have to burst out for certain capacity, for certain workloads into this alternative cloud. And how do you marry those approaches together? I mean, there's no like silver bullet here. There are a few projects like Submariner, some multi-cluster Kubernetes management solutions which help with this. They don't completely. There's a lot of interesting complications in terms of how those clusters communicate, and especially where the data sits. If you start pulling from, again, like taking Amazon as an example, they will charge you through the nose for egress. So you have to think about those things. And if you can make your infrastructure multi-cluster aware from the get-go, so it's not necessarily has to be managed on the Kubernetes layer, but kind of an application layer, that makes things a lot easier. All right, and then I will pass it to Riley, who will talk about more specific things that do at Autodesk with LLMs.
Great. So my name is Riley, and I work as an ML platform engineer at Autodesk. And I'll be talking a little bit about how we've been able to leverage a lot of the little goodies that Oleg described associated with Metaflow in our ML platform. So a little bit of context about our organization. So for those who are unfamiliar, Autodesk is a multinational company that specializes in creating software that basically empowers our customers to design and make across various sectors, including manufacturing, construction, engineering, and media entertainment. Among our most popular software are AutoCAD and Maya, where Maya is being extensively used in visual effects for feature films. Autodesk software serves architects, builders, engineers, designers, manufacturers, 3D artists, and production teams globally. And our innovative design and creation technologies cater to a diverse array of different industries, aiming to support innovators worldwide at scale. So AI and ML are active and expanding areas of focus in both research and product engineering at our company. Numerous product teams at Autodesk aim to innovate by harnessing AI and ML, basically to introduce intelligent capabilities for our customers. The Autodesk AI Lab was established in 2018, and it's a research unit dedicated to applied research, often collaborating with academic institutions like MIT. The lab has contributed over 60 peer-reviewed research papers with past research efforts revolving around problems in the 2D and 3D geometric design space. And the team produces some fascinating work on using language to communicate the semantics of geometry to make design work more intuitive. So I'm part of Autodesk machine learning platform team focused on building a unified ML and AI platform. Our goal is to offer comprehensive tooling across the entire ML, end-to-end ML workflow, enabling data scientists and ML engineers to accelerate model development from research to production. So earlier this year, our team assessed various ML frameworks, and basically we selected Metaflow as a foundational part of our infrastructure due to its human-centric design, and it aligns with some of the preferences of many data scientists and ML engineers at Autodesk who are more comfortable with tooling like Jupyter Notebook and Python. Given the diverse problem space at our organization, we basically recognize the necessity for a platform capable of evolving alongside these new use cases. We like that Metaflow's extensibility and interoperability make it an ideal framework that can grow and adapt to our platform's evolving needs, enabling us to introduce new capabilities on top of Metaflow. So we really like that Metaflow could be used for a variety of different applications like data, compute, orchestration, and versioning, and all of this suited our needs. Metaflow is particularly advantageous for constructing machine learning pipelines by chaining tasks throughout the entire ML workflow, all the way from data preparation to model training and evaluation. And we've been able to leverage Metaflow's convenient wrapper for utilizing AWS Batch for scaling workflows, particularly in the context of training models. It is also helpful to us that Metaflow also excels in versioning and ensuring reproducibility by versioning flow runs, data snapshots, and artifacts, and it can also serve as a useful experiment tracker. Aside from that, Metaflow has proven to be really versatile for us. While we intended to use Metaflow specifically for model training, some of our users have actually been able to use Metaflow for building and orchestrating data extraction pipelines as well. This is a high-level overview of how we've integrated Metaflow into our managed IDE using SageMaker Studio. We call it AMP Studio, and it basically acts as the productivity suite for developing and training models. In order to access Studio, users interact with a UI, which in turn spins up their personal Studio instance. Once they are logged into their Studio notebooks, they have access to Metaflow, which they then leverage to create and orchestrate their jobs at scale. And they'll be able to monitor their workflows through the Metaflow UI. Additionally, users are able to bring in their own data, and Metaflow and Studio have access to import this data. We also successfully integrated Metaflow into our GitOps workflow, enabling data scientists to deploy their jobs all the way into production. One of our users have adopted this pattern to deploy their data extraction pipeline using Metaflow on step functions, where Metaflow basically compiles and maps their flow to a workflow orchestrator for scheduling. And our users can conveniently conduct local testing of their flows, including local runs. They can perform unit testing effortlessly before pushing their flows all the way to production. So currently, we are using step functions as our orchestrator, but we are in the process of transitioning to Argo workflows as our workflow orchestrator of choice. Our AI lab research team is heavily invested in using Ray to train their models. So we needed to figure out a way to integrate Ray with our managed training infrastructure powered by Metaflow to ease their transition to adopting Metaflow. Ray plays a critical piece in transforming our ML platform into an AI platform. And as such, we work with Outer Bounds to evolve Metaflow's compute layer such that we could orchestrate the creation of a transient Ray cluster using AWS Batch multi-node parallel jobs through Metaflow. And in this way, Batch handles the infrastructure, setting up the driver and workers, while Ray optimizes the hardware usage. So currently, we're creating the Ray clusters on top of AWS Batch, but our team is also in the midst of working with Outer Bounds to add compatibility with Kubernetes as well. We used the existing abstractions from the parallel decorator and then teamed up with Outer Bounds to introduce the Metaflow Ray decorator, which basically is like an extension or plugin. And this Metaflow Ray decorator can essentially decorate a step and subsequently sets up the necessary hardware using AWS Batch multi-node parallel jobs. Users then insert their Ray code in the steps, and then during execution, Metaflow starts up the transient Ray cluster, runs the Ray application, and then subsequently shuts down the cluster upon task execution. And thank you very much. Happy to entertain any questions and answers as well.
We've got a couple of minutes if anybody has any questions. Oh, sorry for the microphone.
I have a small question. I only present in Amazon Cloud.
So Metaflow by itself was originally built with AWS as a kind of primary target, but it's actually flexible enough that we have Azure and GCP support as well. You can technically use it on an on-prem cluster as well, so it's not super strongly tied to anything specific.
Kind of an obnoxious question, but meant in a friendly way. Given it seems like shoehorning AI ML into Kubernetes is a bunch of challenges, so why use Kubernetes? I'm just sort of, why not just set aside a cluster of GPUs and just run it that way?
Well, so the Kubernetes is really flexible for those things, so it's really, I think, for me personally, it's mostly the configuration management platform. If anything else, it's not necessarily like about containers, it's just how do you manage applications and like those distributed fashion. And I mean, I've been using AWS Batch for years. Before this, I've been using, just ad hoc containerized platforms. We actually built one at one of the previous companies. And kind of the scheduling containers on servers is usually not the hardest part. It's actually everything around it. When you start thinking about networking and different types of scheduling and auto-scaling, that's where it gets complicated. And Kubernetes happens to have a lot of momentum behind it. And there's a lot of open source projects that help with those things.
Got it. OpenAI uses them, so it can't be it can't be that bad. It was just more.
Yeah, exactly.
I guess this is a question for the second speaker probably, but I was just wondering, you went into kind of how Ray is in your platform and you can spin it up, spin it down. I was wondering, do you also use Ray for production inferencing, or can you speak to?
Yeah, so right now we're focusing on Ray for training because our AI Lab research team is right now working on the training stage, but we are definitely looking to use Ray for inferencing in the next phase, probably in the next fiscal year. Right now our research team is kind of experimenting. I can't really divulge too many details because it is kind of proprietary, but they're basically trying out different models using different deep learning techniques, and they're not at the stage right now to move that into production, but we definitely are looking into leveraging Ray for inferencing for sure.
Are some of the models trained in Ray, are they able to be deployed in the production inferencing environment you have right now? Is that using SageMaker? Is that correct?
I didn't capture.
I was just wondering whether the models that you train with Ray, whether you have a path for them to be deployed outside of Ray, like in SageMaker.
Yeah, that's actually exactly what we're using right now for our more basic models, where we're using SageMaker endpoints to deploy. But we definitely need Ray for more complex use cases, which we anticipate in the next fiscal year.